Hi, I'm Gordon Wettstein, an assistant professor of electrical engineering at Stanford University, where I direct the Computational Imaging Lab. What I'd like to do today is show you an overview of some of the recent projects that we've been working on in my lab. Before we dive into that, let me start by giving you a historical example for, innovations in photography. Back in 1878, Leland Stanford had a bet with some of his colleagues on the question whether there was ever any time where the horse had all 4 feet up in the air. In order to prove his point, he hired the experimental photographer Edward Muybridge to capture photographic evidence, and what you can see on the upper right is that Muybridge was indeed able to capture this photographic evidence. And what he did to do that is he created this experimental imaging system. You can see in the background, these are many cameras mounted next to each other. They're all connected to mechanical shutters that are, again, connected to these tripwires. So as the horse runs across the track, it trips the wires, the shutter falls down, exposes a photograph, and by looking at all the different photographs captured by these cameras at slightly different points in time as the horse runs across the track, you can capture what looks like a high-speed photograph of the horse. So imaging has been part of Stanford's history since the early days, and we continue in Muybridge's tradition and build modern digital photography and imaging systems that use modern electronics and advanced algorithms. Some of the topics we work on include computational cameras, but we actually also work on computational displays, for example, for applications in augmented and virtual reality. Before I dive into these, let me just show you a couple of recent projects that we've been working on for applications in looking around corners or non-line of sight imaging. So here we also built on high-speed imaging systems, just like Muybridge did, but we can make them a lot faster today. Indeed, we can capture light at the speed of light and visualize how light transport operates in free space or in a medium. So here you can see an optical fiber. The optical fiber is kind of wound around in a circle to extend the path length. And what we did here is we take a picosecond pulse laser, connected that to the fiber on one end, and what you'll see is that as you shoot a laser pulse into this fiber, here shown as a transient image, we can actually visualize how this laser pulse propagates through the fiber, because at any point in the fiber, a few photons will actually scatter out of the fiber, and the camera can capture this. But it's only able to capture this dynamic nature of light if it actually operates at picosecond accuracy, and it can timestamp the photons that reach the camera, which is exactly what we did. So here, again, we use a picosecond laser that shoots short pulses of light into the scene at a million times per second. These light pulses will sometimes be directly reflected to the detector. Sometimes the light bounces around in the scene before it reaches the detector. So this is the indirectly reflected light. We built on modern single-photon sensitive detectors that are known as SPADs. And these SPADs can not only detect one photon of the returning pulse, including the directly and indirectly reflected light, but they can also timestamp it with picosecond accuracy using a time-to-digital converter. So this SPAD is able to timestamp a single photon event out of this entire pulse that returns to it. And by repeating the experiment many times, and maybe using an array of these detectors, we can build up histograms with each of them by repeating the experiment, and these histograms look very similar to the shape of the returning light. Building on this new and emerging sensor technology, we can then develop advanced algorithms to process this to enable new imaging capabilities that I'll show you in a second. So where is this useful? Well, pretty much all LiDAR and 3D imaging systems that you see out there use this principle of operation, this time-of-flight imaging, where you shoot a laser pulse into a scene, you measure how long it takes for the light to return to the detector, and that tells you how far away a point is. And then you can scan that over the scene to get a 3D image, or a point cloud. So this is what makes autonomous cars drive and see the world around them in 3D, but they kind of fail if they can't see an object. For example, if it's occluded by some type of a light-blocking occluder. Well, we can build advanced computational imaging methods that can overcome this shortcoming and actually see around corners. So let me give you an intuition of how that works. We use the same pulse laser and time-resolved detector to shoot laser pulses into the scene. Some of the light that goes into the scene will be directly reflected, and some of the light will be indirectly reflected because it bounced off of the visible surface into the hidden part of the scene, back into the visible part, and then to the detector. So we don't know exactly what the shape is of this indirectly reflected light or the geometry of that scene, but we know that the time of flight of the directly reflected light, for example, in this case was 2.7 nanoseconds, which corresponds to a time of flight of about 40 centimeters. Looking at the time of flight of the other indirectly reflected light, we know that there's something behind the corner at a distance of about 24 centimeters, based again on this time of flight, but we don't know where it came from because all the light or all the objects on this arc would have resulted in the same time of flight. So we need to build inverse methods and advanced algorithms to disentangle these representations. And indeed what we do is we scan the indirect light transport on multiple different points on the wall over this imaging area that you can see here, and we digitally remove the directly reflected light because it doesn't tell us anything about the object that's hidden behind the scene. And then we get measurements that kind of look like the 3D cube on the upper left, which includes the time-resolved indirect light transport of the scene, in this case of the bunny. Here's an example of experimentally measured data that we published in our Nature 2018 work. And what you can see here is that this time-resolved light is captured. It doesn't really look like the 3D objects at all. And then using advanced algorithms like our light cone transform, we can turn these measurements into a 3D representation of the scene. And indeed, we can do so very efficiently and in real time. So these were some of the earlier results. Here's an updated version of our imaging system. On the left-hand side, you can see a hidden scene containing a statue, a plant, and a table. There's an occluder and our imaging system on a little card. On the right, you can see that the imaging system really just scans the wall. It doesn't actually see the hidden scene at all. Here we cheated a little bit and took a camera and put it behind the occluder. So what you can see here is these indirect reflections from the wall towards the statue, the plant, and the table. And these indirectly reflected photons are exactly what we're looking for because these carry all the information for us to be able to recover the 3D shape of the scene. The measurements here look kind of like this. You can again see these ripples, look like ripples on a pond when you throw a rock in them, but this is really just a time-resolved indirect light transport of the scene. You can also see the wall, and that is because we captured these data in indirect sunlight, so some of the ambient photons come in, don't really carry in information, and they actually corrupt our measurements. Nevertheless, our algorithms are very robust to ambient light and other artifacts, and they're able to estimate the 3D shape of the scene, seen here on the right, at a pretty high fidelity. So it's really possible to build an imaging system that can see around a corner today. So how do we do this? Well, in this particular case, we work with the time-dependent wave equation that you can see here, and what we realized is that this non-line of sight problem is actually a boundary value problem, where we measure one boundary value, one boundary condition, and we want to estimate the other boundary condition. So specifically, we measure the time-dependent light transport on the wall, x, y, but we lost the information over z. So z equals 0 is just the plane on the wall where we take our measurements. And what we want is the time-independent light transport of the hidden scene in x, y, and z. So this basically models the hidden scene as a set of point emitters that all emit a spherical point at time equals 0. And we have been developing fast range migration techniques to migrate with this one boundary condition to the other boundary condition for this 3D shape estimation. So here's another example where we take measurements of a full room-sized scene that contains a statue, a glossy dragon, a bookshelf with multiple different objects. And what's interesting here is that all these objects have different reflectance functions. For example, the statue is diffuse, the dragon is glossy, and the disco ball is highly specular and is composed of these little facets, of these little planar facets. So this is our hidden scene. Again, we measure x, y on a visible wall, not directly the scene, but we take these indirect measurements. They look kind of like this. I can play them back in time again. You can see these little dots in these measurements. These dots are actually the light reflected off of the disco ball in the hidden scene and reflected back towards the visible wall. So when we play this back in time, again, this measured data looks really incredible. We can see these ripples on the pond. This is the time-resolved indirect light transport of diffuse objects, but then we can see also these points that are basically the facets of the light reflected off of the mirror arriving at the wall at different points in time. So in our 2019 SIGGRAPH paper, we developed this range migration technique that's known as FK migration to then take this data and directly estimate the 3D shape of the scene. And the unique part here is that this method is really robust to all these different reflectance properties of the hidden scene. When Ramesh Raskar at MIT invented the idea of looking around corners back in 2012, what he had in mind was that you had a person inside a room and you had a camera outside the room, and the camera would take a picture of the door as it's open and basically see around the corner. So in some of our latest work, we take this idea one step further and ask whether you can see inside a room with the door closed. Now that seems pretty crazy, but it may actually be feasible under certain assumptions. So in this case, we again take a camera that's outside the room, and we only have access to a single optical path. So light that propagates through the keyhole and hits the rear wall of this room. And it directly reflects off of this wall. Some of the light scatters into the room. It scatters off of the person, back to the wall, and then some of the photons will actually come out the same optical path as they went in. And so we call this problem keyhole imaging, and it's significantly more difficult than non-line of sight imaging, simply because you can't scan on the rear wall. You can only have access to a single optical path. Now, this seems impossible unless there's some kind of motion of the object in the room. And now the problem is to simultaneously estimate the motion of the object together with its shape. So it seems kind of crazy, but it may actually work, at least to some extent. So here's a physical object, this mannequin, and some measurements that we took for the mannequin. Again, when it's not moving, we just get a 1D histogram that shows how many photons arrived at what time relative to the emission of the laser pulse. And you know, that's too little data to really recover the shape of the object. But as soon as we move the object along an unknown trajectory, we get some diversity in these measurements. And you can see that the shape of these histograms actually changes. Now the thing is, like, again, we don't know where the object actually moved or how it looks. So we've been developing algorithms using expectation maximization to simultaneously estimate the 2D shape of the object and its motion trajectory, which you can see on the right. The motion trajectory is recovered very well, and it's surprising that we actually get a shape that resembles the mannequin, despite the highly ill-posedness of this inverse method. Here you can see a couple of other results of characters. Again, we use physical measurements to estimate the 2D shape of these objects, where you can clearly see the shape of the characters. You can make them out. And the motion trajectories are estimated simultaneously, and they all look pretty decent for such a challenging problem. Okay, let me introduce you to another topic that we're working on in the lab, and I call it deep optics. It's based on modern machine learning techniques that are used in image processing and computer vision. Typically, we learn an algorithm, represented here by this neural network. We have some training data, we send it through our algorithm, we calculate a loss function and backpropagate the error into the parameters of the network. So this is what pretty much everybody does in computer vision, and that drives modern imaging systems. Now we take this idea one step further to jointly optimize the physical parameters of the camera and the reconstruction algorithms, end to end. So this may be useful to optimize imaging systems for specific tasks. So for example, if the camera's only task in life is to classify cats, then maybe there is a better lens or better sensor or better low-level electronics that can help optimize the performance of this camera for this specific task, or that alternatively make it thinner, smaller, lighter, more power efficient, and so on. So there are many different benefits of this end-to-end optimization approach. Now, you can interpret this in multiple different ways. I typically like to think about it as a physical layer and a digital layer that we can train end-to-end in simulation. So that requires us to have a differentiable simulator of the physical layer. Once we've trained this physical layer, we can fabricate it, for example, by fabricating a custom lens that we may have optimized, or to change the sensor electronics. And during inference, the physical layer stays fixed and the digital layer does most of the work. So now, again, you can interpret this as an optical encoder, electronic decoder system, where the optics, encodes the information on the sensor and the electronics decodes it. Or you can think about it as a hybrid optical-electronic neural network, where some of the computation is already done in the physics, in the physical layer for you, and the digital layer doesn't have to do that anymore. So this may be useful for saving power or improving the latency of your imaging system. We've looked into this topic for multiple different problems. Here I'm just going to highlight one where we optimized a thin diffractive optical element that you can see here. It looks kind of crazy, but this optical element is optimized by a machine learning algorithm. You can drop it into the aperture of a camera, and this camera will then do the following. It will take an input image that comes in from the left, and it will optically copy this image into, in this case, 16 copies of the image. Each one is blurred or convolved by a different convolution kernel in optics at the speed of light, basically. And what that does is it implements a single layer of a convolutional neural network in optics. We have an additional fully connected layer in the digital layer that then does the classification. And what that allows you to do is you can get twice the classification accuracy for the same power budget, which is really important for edge devices, for example, your camera on a drone, or you can reduce the power consumption by a factor of 2 for the same classification accuracy as a fully digital system. So this idea of deep optics really opens up a lot of different applications. The last topic I want to briefly discuss today is that of computational displays for applications in AR and VR, and also for wearable computing systems. So when Charles Wheatstone invented the stereoscopic viewing apparatus that you can see here in 1838, he had no idea that more than 150 years later, this is really a hot topic in engineering and one of the National Academy of Engineering's grand challenges of the 21st century. So enhancing virtual reality systems is important, and current systems that are available on the market actually operate in a very similar way to Charles Wheatstone's original systems. You have a microdisplay in your head-mounted display that you can see here. That's, for example, a phone screen, and you observe it through lenses that very much act like a magnifying glass. So what you actually see is a magnified virtual image that appears at a fixed distance away from the user. You can predict exactly where that fixed distance is using the Gaussian thin lens formula, and that depends on the physical distance between the microdisplay and the lens and the focal power of the lens itself. Now, this is not a natural viewing condition because each eye basically is looking at a plane floating in space in front of it. And this fixed focus design is different from the real world because in the real world we have 3D objects at all different distances from the user, and the user can focus their eyes or accommodate them at multiple different distances. If you don't support these focus cues in VR, that can lead to nausea, eye strain, and has many different problems associated with this divergence accommodation conflict. In our lab, we've been working on many different technologies to address this, including varifocal displays, near-eye light field displays, and accommodation invariant displays. I don't have enough time to really dive into the details of all of them, but I just want to highlight one of the simplest and most practical approaches to solving this using varifocal displays. So a varifocal display is one that has a dynamic focal plane. And there are multiple ways of achieving this. One way is to actuate the microdisplay inside the head mount that you can see here. With a few millimeters of optical actuation, you can actually change the magnified image distance by a very large range, over the entire range that you want. Now, this assumes that you have access to eye tracking. So if I know what point the user is looking at and how far away that is, I'm just going to move the virtual image distance to that distance. We verified that this really achieves natural viewing conditions with an early prototype back in 2016, where we hacked a Samsung Gear VR with a motor and eye trackers, and we can dynamically drive the focal plane at at the same rate at which the human visual system changes its accommodation, which is pretty slow, but 300 to 500 milliseconds for a change in accommodation over a pretty large range. We've also built benchtop setups that use reference machines or instruments like this autorefractor that you can see here to verify with many user studies that users using this varifocal mode can naturally accommodate at multiple different distances. It's really reassuring to see that some of this technology has in the meantime migrated into prototypes that, for example, Facebook's working on. So over the last few years, they've been announcing their half-dome prototype that actually uses this mechanical actuation mechanism I described earlier. And that's something that we'll probably see in upcoming products. So it's great to see this transition from research efforts into actual products slowly happening in the commercial world. Now, what I mentioned is that, these varifocal or other types of focus supporting near-eye displays can really give people with normal vision a much better experience in VR or AR. And much of that is driven by this idea that, when the eye is healthy and the lens inside the eye can deform to bring objects at near distances and far distances in focus, we just need to be able to present the optical stimulus to the user at these distances. And we can do that, for example, using these varifocal techniques. Now, one thing to note is that, what if you don't have normal vision? Many of us are wearing glasses, and, the conditions that are most important here are nearsightedness and farsightedness. Well, these can be easily corrected using fixed focal lenses, for example, the ones that I'm wearing right now. So they just shift the accommodation range back into the normal range. And that's no problem. However, there's a condition known as presbyopia that hits all of us at a certain age, for example, after about 45 to 50 years of age. The problem here is that the lens inside of our eyes gets stiffer with age, and they at some stage can't deform anymore. And what that means is that we have a very limited accommodation range, and we can only see objects in the real world at one fixed distance in clear focus. So just to illustrate what that may look like, here's a scene that contains a book that's very close by and another office scene that's farther away. So with normal vision, you can accommodate your eyes at all these distances, and you don't even notice how the autofocus mechanism of your eyes will dynamically adjust the focus of your eyes. A presbyope, on the other hand, may be able to see the far distance correctly, but they can't read at all. So because their eyes cannot accommodate or change the focal power to match this distance. Now, there are many existing prescription techniques that allow you to fix this. One of the most common ones include reading glasses. So you can buy inexpensive reading glasses in the store, you put them on, and now you can read. But the problem is that you've just shifted your focal plane forward. You can read, but you can't see the distance anymore. And that's a problem. So you need to put your reading glasses on and off if you want to look at different objects. There are progressive glasses that have a varying focal power over the lens itself. And that means if you look through the top part of your lens, you can see far well. If you look through the bottom part of your lens, you can see near well. The challenge with progressive glasses, however, is that they first of all distort the real world. And second, the field of vision, the part of the scene that you see at any given distance in focus, is severely reduced compared to the entire visual field that you once enjoyed. So progressive glasses are far from ideal. The natural solution is actually to just look at an object and that object coming into focus, which you can kind of see here. So we would like to have a technology that allows us to just look at an object and then do the refocusing for us. So this is something we've been exploring in our lab for the last few years, and we call this technology autofocals. It looks very much like a head-mounted display. This is one of our really early prototypes, which we've in the meantime miniaturized also. So this autofocals system includes stereoscopic eye trackers. This early system also included a depth camera that can image the 3D world in front of it. There's a focus tunable lens that can dynamically adjust its focal power. This lens has some aberrations that we need to correct with the second element. And then there's an offset lens holder that allows us to correct for nearsightedness and farsightedness or astigmatism that can be corrected for with fixed focus lenses. Now, the idea is that we just read the eye tracker, estimate the relative angle between your eyes that tells us how far away the object is that you're looking at, and then we adjust the focal power of the lenses to bring that object into focus, which you can see here. We have done a lot of user studies using this technology, and with these user studies, we've demonstrated that this technology is a lot better than existing prescription glasses by improving the visual acuity of the user over multiple different distances and by improving task performance compared to other prescription glasses. So this is a really effective technology that's really exciting to think about in the near future. As I mentioned before, we're working on a couple of other techniques and areas like neural rendering, computational displays, and other things. So with this, I'd like to thank you for your attention. I'd like to thank my group for doing a lot of the hard work. And again, please visit our website if you'd like to know more about our latest projects and ideas. Thank you so much.